I've been reading the Rust book recently, specifically the chapter about a multi-threaded web server, because it's relevant to some ideas I have. And in that chapter, you develop a basic thread pool to handle concurrent requests to the web server. And a thread pool implementation is something that is useful for a lot of programs, so I decided to extend the implementation in the book a little bit, both to make it useful to me, but also to just learn about thread pools, because I've never really had to implement a thread pool. And here is that implementation. So I have a notion of a job ID. The reason I have that is because I want to be able to wait for specific jobs. And then the job itself is a pair of a job ID and then just some function. This is using the same type as in the Rust book. And it's just a function that you can run once. It doesn't return anything, doesn't take any input. So all the data it needs from the main thread, it has to copy. And here is the thread pool struct. It has some workers. It has a sender, which is used to send jobs. It has a receiver, which receives job IDs. So whenever a job has finished, it will send its the job ID for that job back to the thread pool, so it like knows that this job has finished. Then it has a set of active jobs, and then it has a current ID, which is used to assign new IDs to incoming jobs. These are both behind a ref cell because I want to mutate them, but I want the user of the thread pool just to have a single reference. They don't have to worry about mutability. So this thread pool definitely cannot be used in a multi-threaded setting, but other than that, it should be fine. Then there is the new function for creating a new thread pool. It doesn't do anything special with respect to what's in the book, so I'll skip that. In the execute function, I first take what should the next ID be. I make a job consisting of the job ID and the function that I get as input up here inside a box. Then I indicate that this new job is now active. I increment the current ID, and then I send the job via the channel. And then I return the job ID so the user of the thread pool can know that this job was assigned this ID, and if they want to wait for it later. I also have a wait all function, which looks at the active job IDs, and when there are job IDs, when there are any active job IDs in that set, it will look in the job ID receiver and try to get everything out. So you can see here it waits for a job ID and then it removes it from the active job IDs until there are no more left. Then I have a function to wait for a specific job ID. I'm gonna skip that because this is something I asked ChatGPT to implement, and it didn't necessarily work. Then there is the drop implementation for thread pool. It's also the same as in the Rust book, so I'll skip that. And then I have the worker implementation. It consists essentially of an infinite loop that looks for a message. A message is a job ID and a job. Then it will run the job, and then it will send back that now it's actually finished this job. So the thread pool can know that now the job is finished. And then I have some tests. So that's basically the implementation. So there is a lot of hype right now about ChatGPT, and especially the new GPT-4 backend that came out a couple of days ago. And I think the use of large language models is definitely something we'll see more of in the future. I quite like using GitHub Copilot, for example. So generally I want to experiment with ChatGPT or other language models and try to learn how it can be used. So as I already mentioned, I tried to use ChatGPT to improve this implementation, maybe I could learn something, because I'm definitely not a threadpool expert. And I want to show you how it went. So I have a subscription to ChatGPT, which means that I can use the new backend, GPT-4 backend. And so here's the results. I wrote, I have made a threadpool implementation Rust. Can you suggest improvements to the code? And then I pasted the code. And you can see here the wait function was at this point a to-do. And the rest is more or less the same. And here's what ChatGPT says. The implementation looks good overall. Thank you. So, suggestion number 1, use an atomic count of a current ID instead of ref cell. This prevents panics when updating the counter. So it's referring to this comment, I think, that I had here. This will cause issues if the number of jobs exceeds the maximum value of the usize. But I'm actually not sure what it did prevented that. And then implement the wait function. Yes, that's a good improvement. I had that as a to-do. Add a function to gracefully shut down the thread pool without waiting for all the jobs to complete. That is also a good idea, but actually it's not possible. There's no way in Rust to kill a thread. So while it's a good idea, you cannot really do it. But anyway, so here is the first change I want to highlight. It has decided to, instead of a ref cell, put the active job IDs and the current ID inside an ARC mutex. Now, ARC and mutex are something that's used for sharing things between threads. So in that sense, it's kind of relevant to what we're doing. We're doing threading, so it's relevant to use these types. But they are definitely not appropriate to use on these guys. These should not be shared between threads. They should only be used on the thread where the thread pool exists. And that should also not be used between threads. I mean, it's kind of like the mothership, the controller of all the workers. It should not be shared. That's just like a bag of worms to get into. Okay, so that's something I would definitely consider a mistake. Maybe if you think differently, leave me a comment. Then there's the wait function. So it has an infinite loop, and it checks if the job ID if the job ID is not inside the active job IDs, then it will break. That's fine. And then it will listen to the receiver for job IDs and remove it from the active job IDs. That is kind of correct, with the exception that the data types for this stuff is wrong, but the code itself is fine. And then it has this shutdown method, which drops the thread pool's job sender, and then it will loop over the workers and access a sender on the worker and send a none message. So this concept of a sender on the worker, which is also here, I did not have in my implementation. So it's kind of interesting. Let's see how it's used. So here we have the new function. This line is new, so it's making some message channel inside the new function, and then it has a receiver end of the channel, and then it's listening on the receiver for a job, for a non-message, or for an error. And this is the sender up here. So now it's decided that you can send a message to this receiver of none, and that will stop the thread running. But actually, if you have a long-running job, you cannot kill the job, so it doesn't change anything in that sense. Like that's what I would want for this shutdown, is just to if you have a long-running job, it will just kill the thread and then and exit the program. But you cannot do that in Rust, as I mentioned. So that's the first thing. I'm not really sure it's doing something new here. Yeah, you can exit, you can kill the thread without dropping the sender, which would not be possible before. But how big an improvement that is, I'm not sure. Now, another thing is that this receiver that I used to send jobs before, or receive jobs in the thread, it's completely ignored. So it's saying here, rest of the threadpool methods, rest of threadpool implementation. That implementation is now buggy because it's trying to send jobs through this receiver, into this receiver, but the thread is not listening to jobs on that receiver. So I told it doesn't make sense to use rcmutex for active job IDs and current IDs because they should never be shared across threads. As I said, you also forgot about the receiver argument to work on new. The receivers used to get jobs, as I just said. And then ChatGPT thinks I'm correct. It fixes up this thing, and then it makes a new wait implementation, which is now wrong in the sense, or it's buggy in the sense that if you wait for the same job twice, then the second time it will hang forever because it has an infinite loop. It listens to the receiver to new incoming finished jobs, and then it removes that incoming job from the active jobs. And if the job it received is equal to the one it's waiting for, then it breaks. But if I already waited for that job, then this is just an infinite loop. So I told it that your implementation will loop forever. And then it came up with this one, which is like very verbose. You don't really need this finished variable and things like that. But at least now it's correct. But I think that at this point, I'm doing all the thinking anyway. And in terms of how much I had to type, it's almost faster just to type the correct code myself. It probably is faster. And also I don't have to think about how to communicate with some language model. I can just write the code as it should be. That being said, there may come a point where large language models can code well. I still don't worry about being unemployed, however. I think programmers will simply move up one level of abstraction and focus more on ideas or what to do rather than how to code it. In some ways, I think it will be analogous to the move from assembly language to C, where you move from very low level things to a high level of expression. There will still be interesting things to think about and things to build. We'll just do it via a new interface to the computer. But even so, I think there will still be a need for Python, Rust, Java, or whatever developers, just that we still need people to write assembly today. Some things the large language models won't be able to do because they've never seen it before, or because we need manual verification of the LLM code. Whatever happens, at least we're living in interesting times.